Welcome to the presentation on E2 E3 CM module, Site Planning, Relocation and Rrh. Cell Planning Objectives: Minimize TCO. In addition to minimizing the overall network cost, this objective may also include minimizing economic cost related to deployment costs and parameter optimization. Maximize capacity. Maximize coverage. Minimize power consumption. Optimize handover zones. In a well-planned cellular system, a certain proportion of the area of each cell should overlap with neighboring cells to satisfy HO conditions. HO zones are essential to guarantee continuity of service between the sectors. It also strengthens the radio link against fast fading and shadowing. However, too much overlap may result in wastage of power and radio resources and increase in interference and electrosmoke, making it a tricky planning objective. Cell planning inputs. Different inputs are required to solve the cell planning difficulty depending on objectives in focus and phase of planning. Usually, the following inputs need to be known. Traffic models. User traffic distribution is a main factor that ultimately determines the cellular system plan and hence is a key input in the CP process. In GSM, for instance, geographical characterization of traffic distribution is sufficient. However, with multi-service systems supporting data traffic characterization based on types and level of service is needed. These test point based traffic models are often used for CP traffic modeling for the sake of practicality. Potential site locations. Theoretically, a base station can be installed anywhere. However, in the real world, a set of candidate sites is first predetermined and used as input to the CP to incorporate the real estate constraints. The objective, thus, is to find the optimum subset of BS locations. BS model. There are many parameters that dictate the BS model such as antenna type and height, receiver sensitivity, load capacity, transmit power and capital and operational cost. Propagation prediction models or maps. A key input to the planning process is the signal propagation model. The potential of this model is to incorporate reflection, differentiation, absorption and propagation of the signal in real environment, taking into account the natural and man-made structures, vegetation and topography of an area highly determines the accuracy of the CP outcomes. Very sophisticated planning tools rely on actual measurement based propagation maps or ray tracing based complex analysis to predict the propagation. However, obtaining complete propagation maps of a large area using these methods is a very cumbersome, time consuming and expensive process. For this reason, different empirical models have been proposed in the literature. Such models abstract the experimental and statistical data in the form of deterministic expressions that can easily be used in the CP. Okumura Hatta and Cos 231 are a few examples of such well-known propagation models used in CP to depict propagation laws in different environments and scenarios. A fine-tuning of these models is done by setting parameters within these models to reason the real-world conditions as closely as possible. While propagation models for sub 5 GHz frequencies are well established, research on developing such models for higher frequencies such as millimeter waves is still in progress. Cell planning outputs. The goal of the CP process is to provide one or more of the following outputs: the optimal number of base stations, the best locations to install base stations, the types of base station optimal for each location, the configuration of parameters such as antenna height, number of sectors, and sector orientation, tilt, power, etc. Frequency reuse pattern, capacity dimensioning. Example, number of carriers or carrier components per sector. Types of cell planning. The objectives, input and output of the CP process also depend on the type of planning. There are generally two types of cell planning: rollout and incremental, and that is the first one, rollout CP. This is the CP where no prior networks exist and a plain state approach can be used to meet all the objectives of interest. In terms of input parameters, in this phase, the traffic distribution is not exactly known yet. Estimates of traffic based on geomarketing forecasts are used for planning in this phase. Incremental planning. This type of CP is generally carried out after the first rollout planning to meet the increased demand. Unlike the planned state approach, planning in this phase is bounded by additional constraints imposed by existing sites. However, in this phase, the traffic distribution can be modeled now with much better accuracy using the measurements from existing network reports. It is anticipated that 5G deployment will mostly require incremental planning by building on LTE, UMTS, GSM network. Site relocation and RRH. To answer the need for more throughput at lower cost, wireless network providers are moving to using a remote radio head where the radio equipment is connected to the baseband unit by a fiber optic cable. This provides a new level of flexibility in how the cell site is deployed, including siting the RRH at the masthead or locating the BBU at a remote location. Remote radio heads have become one of the most important subsystems of today's new distributed base stations. The RRH concept constitutes a fundamental part of a state-of-the-art base station architecture. The move to RRH-based cell sites has delivered flexibility, performance improvements, and cost savings. RRH technology. The RRH contains the base station's RF circuitry plus analog to digital or digital to analog converters and up-down converters. RRHs also have operation and management processing capabilities, and a standardized optical interface to, to connect to the rest of the base station. Modern interfaces standards for RRH interconnect are Open Base Station Architecture Initiative OBSAI and Common Public Radio Interface. The same RRH architecture can be visualized from the figure given here. RRH functions. RRH is sitting on top of cell tower that mainly performs the following functions: convert optical signal to electrical signal and vice versa using CPRI, that is Common Public Radio Interface. In transmitter section of RRH, it converts digital signal to RF and amplifies that signal to the desired power level, and antenna connected to it radiates the RF signal in air. In receiver section of RRH, it receives the desired band of signal from antenna and amplify it, and it converts RF signal back to digital signal in the receiver chain. The RRH architecture can be visualized from the figure given here. It consists of DUC, that's a digital up conversion, digital to analog converter, and power amplifier in the transmitter path, and in the receiver path we have DDC or digital down conversion, analog to digital converter, and low noise amplifier. And here we can see the OPSI or CPRI interface, which is connected to the digital baseband signal processing or BBU, and the media usually used is optical fiber. RRH is connected to the baseband unit via fiber optical cable which uses CPRI format signals. The key advantages of using RRHs are listed below: smaller footprint, easier installation, reduced wind load, lower site rental costs, and optimized coverage. Then flexibility in software, remote upgrades and frequency agile operations, easier capacity upgrades, higher performance, high power efficiency, spectral emission requirements, sensitivity and capacity, multi-mode operations, combined and concurrent multi-standard operations reduce equipment needs, flexible multi-carrier capability, frequency agility, easier capacity upgrades. So these are the key advantages of using RRHs. Cell site evolution, antenna integrated RRH. Features of antenna integrated RRH. Less signal transmission loss between RRH and antenna. Less capex or opex burden on operators. Reduction of physical load on frame structures. Passive intermodulation disto quality. CRAN or Cloud RAN. Cloud RAN is a specific concept that is rapidly being deployed and prepared for commercial deployment. This aims to centralize the functions of the RAN network within the cloud servers such that only the physical transceiver and antenna elements of the E-Node B need to be physically located at the cell site. This provides for a more cost-efficient deployment especially for small cells or local cell sites used to boost capacity or fill gaps in coverage. CRAN. Here we can see the front hole, the back hole, BBU, and the fiber link to the RRH. Distributed base station in CRAN architecture. And the CRAN core is also shown, which is connected to the BBU. In CRAN, baseband unit is a centralized BBU pool and connected to the RRHs. Therefore, few BBUs are needed in CRAN compared to the traditional architecture. CRAN has ability to decrease the cost of network operation and power consumption compared to the traditional architecture. Traditional cellular network architecture. In the traditional architecture, the functions of the radio and BBU processing are co-located in BS, that is in the same cell site. Generally, the antenna is located near to the radio unit. The coaxial cables are used to connect the antenna with radio unit. Further, X2 interface and S1 are used between BSS and connect the BSS to the mobile core network respectively. The same can be visualized from the figure given below, where we can see the X2 interface, the S1 interface, and the connectivity between mobile core network, backhaul, and the radio access network. CRAN architecture. In this context, the BS is separated into two parts, a baseband signal processing unit and a radio unit. The radio unit is called RRH and it has many functions such as digital to analog conversion, analog to digital conversion, digital processing, filtering, power amplification, and interface to the fiber. The baseband signal processing is called a BBU, which is located in a central unit called BBU pool. The interconnection and split function between the BBU and RRH depend on type of the network deployment. The distance between an RRH and a BBU pool is up to 40 km. Distance limitation is coming from the propagation delay of fiber and processing signal in BBU. However, a front hole can be optical fiber or microwave. Generally, the optical fiber is a candidate to be used in the next generation to meet the requirements of data rate demands. Moreover, RRHs designed to be small and light, so easy to install on poles or rooftops with very efficient cooling. Open Base Station Architecture Initiative OBSAI and Common Public Radio Interface CPRI are the radio interface candidate protocols to use between RRHs and BBUs. CRAN components. In general, CRAN architecture comprises of three main parts, namely BBU pool, which consists of a large number of BBUs with centralized processors located at the CO. RRHs with antenna system located at the cell sites, and front hole transport link which connects the BBU pool to the RRHs and needs low latency and high bandwidth to meet the 5G requirements. CRAN deployment. CRAN is a candidate architecture to implement for next generation of cellular network instead of traditional cellular network like LTE Advanced, LTE, and UMTS. In CRAN architecture, BSS can be implemented by separating BBUs and RRHs, and baseband processing resources for multiple BBUs in a CU can be scheduled in carrier level. It is easy to deploy the RRHs as they are lightweight and small in size. RRHs transmit and receive radio signals from and to the BBUs via optical fiber fronthaul links. RRHs can be installed in cell sites far from the BBU pool. For example, it can be from 1 to 40 km. The fronthaul network between BBUs and RRHs can be standardized like CPRI or OBSAI. The centralized BBUs should have a low latency, high bandwidth, corresponding protocol and switch metrics to support the effective cooperation among multiple BBUs in BBU pool. With this, we have come to an end of this session. Thank you all the participants.